Now we'll see various memory designs and we'll try to understand the access time of each and every design. Okay. Now let us begin with this design. Okay. So where you have processor is connected to cache is connected to memory. That is obvious. Apart from that, we will be having same bus size. You see, this is bus. Okay. So processor and cache is connected through a bus whose size is one word. That means we can transfer one word from cache to processor. Again, we can, second thing, we can transfer one word from processor to cache, two-way. Similarly, here you have bus between cache and memory. That's length also one word. Okay. So in this model, what is the cost incurred to access one word we will see. Otherwise, one memory access. So I assume these parameters, one cycle to send the address. That means, so it's all about memory access time. Understand? I'm talking about particularly this memory because we know that this memory is going to have lot of delay, right? Otherwise, getting the data from cache is nanoseconds, right? That means it takes very less time. Whereas that means one clock cycle. But to get the data from memory it takes 20 to 30 cycles. That's why we have to effectively design our memory so that quickly we can access the data. For that I am assuming that let's say there is a cache miss. If there is a cache hit, we don't require to bother about this memory design, isn't it? That's why sometimes there is a cache miss, then at that time we'll come here. Then what we do? Recall. Whenever there is a cache miss, then probably you will be accessing this memory, right? You will be sending the data from memory to cache. Especially you will be sending one block of data. Remember it. Okay, one block, right? Recall. So whenever there is a cache miss, we will send the data from memory to cache, especially complete block. Later we will fetch. Now I would like to talk about this block transfer from memory to cache. How much time it will take? For that I am using these three parameters. This parameter is to send the address because recall everyone. This is DRAM. Okay, that means dynamic RAM. So we don't really require much details about this technology. Just understand that memory is made of DRAM. Cache is made of SRAM, static RAM. Okay. Now, so to fetch data from memory, what we have to do is we have to specify the address and we have to send the address. That's why one parameter is we have to send the address. Assume that, so that takes one cycle. Usually that is the case. So it takes one clock cycle to send address to this memory unit. After that, so this DRAM will give you the data. Before that, what happens? This DRAM has to identify the right location, correct? Because you are specifying it, then that the right appropriate line should be selected, correct? After that, data should be transferred. The time, that is called memory latency. Once you specify the address, then the DRAM, I can say, will find out the data. For that it takes some time, and the time is, let's say, memory latency. Assume that, let's say, it takes 15 cycles for each DRAM access initiated. Whenever you initiate one DRAM access, then that takes 15 cycles. Understand? Once DRAM access is initiated, then when DRAM is ready to give the data, then it will give the data. We have to take it. That is a trivial thing. It takes only one cycle. Finally, three things. One is sending the address, one cycle. Taking the data, one cycle, but in between there is a delay, that is called DRAM latency. That means that device requires some time to get the right data. Understand? So that is called time required to access the initiate the access. Okay, that takes 15 cycles, you remember. So this is bottleneck. We have to reduce it. Now for this design, how much time it will take, we will see. So let us calculate that one. Very simple. Since whenever there is a cache miss, I am assuming block size to equal to, let's say, 4 words. Okay, 4 words. If block size is 4 words, then we know that we are going to transfer the block to cache. Then how much time it will take? First, we have to specify the first address, correct? Because there are 4 blocks, right? Assume that each word takes 1 unit to specify the address. Let me talk about only one word. So to send the address, one cycle, plus for initiating the DRAM 15 cycles, plus to get the data back one cycle. Finally 17 cycles for one word, but we have 4 such words in the block, right? Then it would be 4 into 17, 68 cycles, remember it. So in this design, 68 cycles are required to fetch one block. So what if block size is 8 words? Then it would be 8 times specify the address, initiate your DRAM, get the data. After initiating the DRAM, it takes 17 into 80. Okay, it's a simple formula. Now we will see another design and we'll try to understand in this one. For your block size of 4 words, answer is 68, isn't it? Remember it, 68 cycles. Now let us see the second design. So this is wider memory organization. Let us call it as one word wide memory organization. This memory organization is one word wide. So here this memory organization is wider memory organization. I will tell you why it is wider. You can see this widerness here. So here this cache is designed such a way that this cache, so each cache has, it can send 2 words at a time to the memory. Understand? See the width of this bus is, let's say, 2 words. That means what? So data can be transferred from main memory to cache in 2 units. That means 2 word units, not 1 word. Now again, cache to processor, the width of this bus is only 1 word wide. Okay, so I can say that between processor to cache, I am not increasing the bus width, unnecessary for me, I don't want it, but I want to increase the width of bus between cache and main memory. Then what happens, we will see. Sir, why this multiplexer? I will explain that later. Assume that, let's say, to this time in this design we require multiplexer. Let me discuss that later, because our target is here. Now how much time it will take? So what we are going to do is, now we will be specifying the address. Once we specify the address, then at a time 2 words can be taken. Understand? So what we do is, first time we specify the address. Okay, once we specify the address, it takes how much time? 1 cycle to specify the address. So whenever you specify the address, then the corresponding 2 words will be given to you. Okay, so before that, your DRAM should be initiated again. So initiating DRAM is nothing but identifying the right row, because there is a right row where your data is hidden, right? We have to identify the right row. You can imagine your main memory as a matrix of rows and columns. Now the row size is 2 words. Okay, there are a lot of columns. Sorry, row size is, of course, row width is 2 words. That means number of columns are 2 words. The number of rows are many. We don't know. Then we have to identify the right row. That is called, let's say, this DRAM initiation. Understand? Once you initiate the right word, then we have to transfer it. That takes again 1 clock cycle, correct? Because parallelly we are doing. So because we increase the width word size, then at a time to transfer 1 word or 2 words same now, because the width is increased. It's like, you have a highway, only in that only 1 car can go. Then there is another highway where 2 cars can go. Then you see, let's say the time within 1 hour, 1 car can travel from here to here. Within same 1 hour, 2 cars can travel, right? So that's why the time will not be increased. At the same time here also, within 1 clock cycle, 2 words can be transferred. Understand? Now we will see the total story. First initiate the address. Okay, it takes 1 cycle, and that whenever you specify the address, there are 2 words, they will be transferred. So the transfer time will be, already we know that, right? Sorry, before that we have to initiate the DRAM. That takes again only 15 clock cycles. Okay, 15 cycles to initiate. That means the major goal of initiating DRAM is identifying the right row. Understand? There are some other details we don't require. Then we have to get the data back to cache. See, width of cache and main memory same, then all the 2 words will go like this. Okay, it takes only 1 cycle again. So finally I can say that it requires 17 cycles, but how many times we will be doing that? We will be doing that 2 times, right? 17 cycles, but within 17 cycles of time, 2 words we got. But how many words we have? 4 words. To get 4 words, we require 17 into 2. That means 34 cycles. Understand? So 2 times we have to do the same stuff. but here 4 times we have to do, that's why it is 68, it is now only 34. We have another design this time, that is called interleaved memory. So here this memory is single unit, right? What we are going to do is we are going to divide the memory into multiple parts, and we say that they are all memory banks. That organization is called memory bank organization, otherwise interleaved memory organization, and we will see that, and we will see the time taken for that organization. Okay, now before going to that, let me answer this question again for 8 words. Let me take 8 words and solve the problem. Block size is now 8 words. In both of them, how much time they will take? Design number 1. Then we know that first send the address 1 cycle, and 15 for initiating the DRAM, then 1 for getting the data. But we have to do that 8 times, right? Because 8 words should be transferred one by one. At a time only 1 word can be transferred because of the width of your bus. It would be 17 into 8. I think it would be 126 or 136. 8 7 56 5. It is 136. So 136 cycles. Let us assume your block size, 8 words again, but design 2. In the design 2, whenever there is a cache miss, we will transfer 1 block from main memory to cache. I am talking about that. How much time it will take? That's the question. Okay. Now that is main memory access time. It would be, first of all, specify the address of the first word. First word. So automatically 2 words will be fetched. Correct. So that takes 1 cycle for fetching. Specifying the address. Then DRAM latency, for identifying the row, the DRAM latency is 15 cycles, plus for getting the data back 1 cycle. So finally I can say that 17 cycles, but within 17 cycle we got 2 words. Understand? Now what I want to say is, sir, you specified only one address. Why? Because when you specify one address, from that starting address 2 words will be fetched. That way we are organizing. Understand? Since the row size is 2 words, then if you specify the starting address of one of them, then automatically 2 words can be fetched. It is not compulsory to specify this word address, because they are consecutive. Understand? Such a way we can plan it. So 17 cycles for 2 words, but we want 8 words, then 4 times we have to do that, then 68 cycles. So finally it requires 68 cycles, here 136. That means this design is reducing the time to half, right? That means here, if the time here is x, here it will be x by 2. Simple. Now we'll see the next design. Now we'll see the another organization, interleaved memory organization. In interleaved memory organization, so this is the difference. We have multiple banks. Okay, that means we can use these banks parallelly. That is the only advantage we are going to get. So processor to cache, let's say the bus width is 1 word. Cache to this each and every bank, the bus width is only 1 word. We have only 1 bus. Okay. Now, and at any time, one of the bank can utilize this bus. Understand? Now we have some extra circuitry. Okay. So because of that, it will be achieved. Now we will see how to transfer the block from this memory to cache, so that we can see the delay. What we do is, example, let's say the 4 words, assume that block size is 4 words, and that 4 words are obviously consecutive, right? 100 memory address, 104, 108, 112 are the memory addresses of that words. Understand? So these words I would like to fetch from the memory. What I do is, these banks are designed such a way that when you specify the address 100, okay, and we can specify same address 100 here, okay, then the 100th row, I just imagine that this is the 100th row. Okay, so where the memory address 100, that means the word at 100 is located. Okay, this is actually 100th word. So there is a word at 104, right? That I am storing exactly at the 100th row of this memory. Now 108th memory address is stored here, and 112's data is stored here. That means whenever you specify 100, automatically this row will be selected, and This is the first word, this is the second word, this is the third word, this is the fourth word. All the four words will be in a same row, okay, in appropriate banks. So if that is a model, so how much time they will take, we will see. Now first step, we specify the first address to these banks, so that automatically all that four consecutive words will be taken. Understand? So first specify only one address, it takes one cycle. Then since everyone got address, then these DRAMs will start getting initiated, then everything will show these rows after how many bus cycles, clock cycles, 15 cycles, we know that, right? Then since we have only one bus, then one by one, now data is ready, we have to take it. We take this data first, then this data, then this data, one by one, right? So sequentially, so 4 cycles are required. So finally 15 plus 1, 16, 16 plus 4, 9, 20, right? 20 cycles are required to get the data from this organization. Is it not better than previous two? Yes. So in that way, so these three organizations can be discussed and we can understand the differences. Okay. Now one more thing I have forgotten to tell you. In the second organization, so we had this kind of model, right? Processor, and you have multiplexer, right? So that multiplexer processor had two buses, right? Bus 1, bus 2, right? And we had a mux. So why this mux? I didn't discuss, right? I will tell you. This is your cache. Since this cache is, the width is two words, right? Word number 1, let us say this is word 2, okay? Now to show equally, let's say this is word 1, word 2. Now at any time processor wants only one word, but your cache is having a row size 2 words, right? So to fetch the right word appropriate, I can say in each row this is 0th word, first word, right? Now this multiplexer is going to select one of the word, depends on the address which is specified by the processor, okay? So in that way multiplexer is required, because we have two words in the cache, we need only one word. Then which word you want, left side or right side, that will be decided by multiplexers control lines. Understand? So that is about multiplexer. These are the various organizations. Now we are going to see the memory access times are average memory access time, okay? Average memory access time of a memory system. Given a memory system and hit ratios of every cache and main memory, everything, then we are going to find out average memory access time. That is one important parameter to evaluate the performance of your computer, okay? So we will see that details.